Okay, so in this lesson, you want to find the domain of polynomial and rational functions. Now, those are the only two that we're going to look at in this lesson. Now, you've graphed certain polynomial functions. For example, let's look at some polynomial functions that you dealt with, and we're going to determine why these are called polynomial functions. All right, so let's talk first of all about polynomial functions. One of the polynomial functions that you graphed was this kind of function, y equals, I'm going to put it as y, but remember, if I use f of x or g of x or k of x, that means the same thing as y. But we had y equals 3x minus 1. Now, you know what kind of figure this is when you draw this. This is a line, so this is a linear function. All right, so a linear function is a polynomial function. The other type of function that you graphed was, let's say, g of x equals 2x squared minus 3x plus 1. You had to do that in one of the previous lessons. So remember, this is a quadratic function. That's a quadratic function. And the graph of a quadratic function, remember, is a parabola. So you graph parabolas. So your parabola can either opens up or it opens down. But regardless, you know what a quadratic function looks like. And then a linear function, remember, the graph is a line. But here's the point I want you to remember. When we graphed a quadratic function or a line, let's do a line first. So let's say you had this line, and let's say it was in this coordinate plane. Remember, when we talked about the domain, remember we went from left to right. So as you go from left to right, what do you notice about the x-coordinates? And remember, this is an arrow, so it keeps on going in both directions. What do you notice about the x-coordinates on this graph? Well, it goes from negative infinity all the way to positive infinity. All right, so the domain of a linear function is all real numbers. Now remember, we always put this as an interval, so negative infinity to infinity. Now when you look at the quadratic function, if I were to draw a quadratic function, remember it looks something like this. I'll just go ahead and draw it this way. And remember, this arrow keeps on going, although it looks like it's going straight up. It's not. It keeps doing something like this and like this. But regardless, remember, when you did the domain, when you looked at the domain, when you found the domain, you went from negative infinity to infinity. It was the range for this that was not all real numbers, because remember, in this case, you'll notice that the range has a smallest y value. But the domain is all real numbers. So the domain is all real numbers, negative infinity to infinity. The point is this: when you're looking at any polynomial function, whether it's linear, quadratic, or in this case, I want you to see this. You can't see it very well, but hopefully you can. Cubic, this is x cubed. Now we haven't done anything with graphing a cubic, and this is a cubic function. We haven't done anything with graphing a cubic function, but I want you to notice the domain. Remember, this is an arrow here and an arrow here. You're going from negative infinity to infinity. And you remember, you may say, well, there's no graph on this side. Well, remember, it keeps doing this. All right, so at some point, you will have a graph for this x-coordinate. At some point, for this x-coordinate, there'll be a point on the graph, and so on. All right, so for any polynomial function, the domain is all real numbers. So the domain here is all real numbers. And remember, this is a quadratic, so the domain is all real numbers. All right, so what I need to remember now is this: the domain of all polynomial functions is all real numbers. The domain of all polynomial functions is all real numbers. Now, as an interval, we say negative infinity to infinity. Okay, and it kind of makes sense, because if you do a t-table, for any of these functions, I can use any number for x and I'll get a y value back. So if we look at this one, if x is 0, I get 3 times 0 is 0. 0 minus 1 is negative 1. If x is negative 3, I get 3 times negative 3 is a negative 9. Negative 9 minus 1 is negative 10. If I say 4.6, 3 times 4.6 minus 1 is going to give me, okay, so 3 times 4.6 oops, minus 1 gives me 12.8. So remember, for any real number, I'll get a y value back. All right, so hence the idea of the domain being all real numbers. Okay, so the domain of all polynomial functions is all real numbers. And polynomial functions will look like this. You'll have it'll be a bunch of terms. See, in this case I had 2 terms. In this case I had 3 terms. 1, 2, 3. In this case your terms are 2x squared, a negative 3x, a positive 1. In this one here I have 3 terms as well. Okay. Negative x cubed plus 3x squared minus 2. But you can have more than 3 terms. All right, but the point is this, it's always, each term is going to have this form. It will look something like ax to some power. Then you might have another term that might be, and I'm going to go ahead and use a1 times x to the, another power will be n minus 1, let's say, and so on. So it's a bunch of terms, and then you may or may not see your constant. If there's no constant listed, then the term will be a 0. All right, it's understood to be a 0. All right, but each term is going to have some coefficient times a variable raised to an integer power. I'm sorry, a whole number. So n will have to be a whole number. Okay, so n's a whole number. All right, so notice that when I did this, you had the coefficient is 3, x is raised to the first power, 1's a whole number here, and you have your constant. Here you have coefficient, a real number, it could be any real number, it could be a fraction, decimal, integer, whatever you want it to be. And notice that the exponent here is 2, coefficient is -3, the exponent's 1, and your constant. So each term looks like this, where your exponent's a whole number. And then you have your constant. Okay? All right, so the point is this, that all polynomial functions, the domain is all real numbers. Okay? All real numbers. All right, now let's talk about what a rational function looks like. All right, so a rational function is a function that can be written as a quotient of 2 polynomials. All right, 2 polynomials. So here are some examples. F of x equal 3 divided by x minus 1. That's an example of a rational function. Notice the numerator is a monomial, it's still a polynomial. Polynomial is a monomial or more. This is a binomial. Okay, so you have, notice a polynomial divided by polynomial. You could see something like 2x divided by x squared minus 3x plus 1. So polynomial divided by polynomial. H of x equal x plus 6 divided by 2x minus 5. These are all examples of rational functions. You have a polynomial divided by a polynomial. So it's a quotient. Remember, quotient means to divide, so you're dividing 2 polynomials. All right, now, to find the domain of this, so the focus here is to find the domain, focus, find the domain of a rational function. All right, so I'm going to find the domain of a rational function. All right, well, let's first of all remember this. Remember, if you were to, on your calculator, say 0 divided by 5, 0 divided by 5, notice you will get 0 divided by 5 in your calculator, you'll get 0, okay? But if I did 5 divided by 0, notice what happens. 5 divided by 0, you get an error. So you can't divide by 0. So remember, anytime you divide by 0, that's undefined. Okay? So anytime you divide by 0, that's undefined. So whenever we have a rational function, you got to look to see what makes the denominator 0. because remember, you cannot divide by 0. So when finding the domain, of a rational function, you need to first determine what values will make the denominator 0. Denominator 0. So basically, you're finding the restrictions. Sometimes there'll be, sometimes it's referred to as what values are excluded. What values of the domain? What values of the domain are excluded? Okay. So I guess I could also say what values of the, when I say domain, I got to be a little bit more careful there because your domain here is not oral numbers. So let me kind of rephrase this. Instead of saying what values of the domain are excluded, let's say let me rephrase this as what real numbers are excluded from the domain. Let's rephrase it like that. All right, so what real numbers are excluded from the domain? Okay, all right, so let's look at some examples. All right, now let's look at this. Find the domain of each rational expression, a rational function. Find the domain of each rational function. Number 1, f of x is equal to 2 divided by x minus 3. All right, so notice first of all that this is a rational function, not a polynomial function. Remember, a polynomial function, the domain will be all real numbers. Just like this is a polynomial function, domain is all real numbers. So notice that as you went from left to right, you got every possible, every real number was a possible value in the domain, Here, though, that's a rational function. So first of all, you got to recognize this is rational. That's important. Okay, what makes the denominator 0? So the question is, where is x minus 3 equal to 0? That's your question. Well, when you solve for the variable x, notice this is a linear equation. When you solve for the variable x, you're going to get x equal 3. So what you found was that I need to exclude, so x equal 3 is not in the domain. Okay, so x equal 3 is not in the domain. All right, now you want to also write the domain in interval notation. Okay, interval notation. All right, so remember, I can use any number for x. So if I did a t-table, for example, I just want to show you. So this says I can use any number for x except 3. So if I use a t-table and I said let x be 0, I would get 2 divided by 0 minus 3, which is negative 3. So I get a y value of negative 3, negative 2/3. If x is, let's say, 4, I get 2 divided by 4 minus 3, which is 2 divided by 1, which is 2. So I get a y value of 2. So this is negative 2/3. This is 2. If x is, let's say, negative 3, I get 2 divided by negative 3 minus 3, which is 2 divided by negative 6, which is a negative 1/3. So I can use any number for x except 3. And the reason I can't use 3 is because of this. So if I put 3 right here, I'm going to go ahead and put 3 right here. If I put 3 right here, I get 2 divided by 3 minus 3, which is 2 divided by 0, which is undefined. That's undefined. So the only value of x that makes the denominator 0 is when x is 3. All right, now you want to write this as interval notation, so here's how I would do this. I would just kind of draw a number line like this, put 3, and cross it out because I can't use it. And then I can use every other number except 3. So you're going from negative infinity to 3. Now since I can't use 3, I have to use parentheses because 3 is not part of the domain. So parentheses. Union, because that's two intervals. See that 3 divided the number line into two parts? So you have this interval and this interval. So then you can say union and then 3 parentheses to infinity. So this means every real number except 3. Notice the parentheses there though. All right, so that's your domain. So the domain would be negative infinity to 3, union 3 to infinity. All right, let's look at number 2. Number 2, suppose we had f of x equal x plus 2 divided by 3x minus 1. All right, so notice it is a rational function. I have a polynomial divided by polynomial. And remember, if I want to find the domain, all you look at is what makes the denominator equal to 0. So you got to find out where is 3x minus 1 equal to 0. That's all you got to do. And solve for x. So when I solve for x, I'm going to get 3x equal 1, which means x is 1/3. So 1/3 makes my denominator 0. You can see it. What's 3 times 1/3? 3 times 1/3 is 1. 1 minus 1 is 0. All right, so you found that the domain will be all real numbers except 1/3. Domain is all real numbers except 1/3. Okay, but you want to put this in interval notation. So let's put this on the number line. 1/3, cross it out, and then your domain would be all of these numbers, all of these real numbers, and all of these real numbers. So you're going from negative infinity to 1/3 with a parentheses. Remember parentheses because 1/3 is not part of the domain. Union, and then you say 1/3. Then you do this interval, so that's 1/3 to infinity. All right, so remember this means all real numbers except 1/3. Okay, so that's your domain. All right, it's not that difficult. It's fairly easy to deal with. All right, let's look at number 3. Number 3. So number 3, let's suppose you had g of x equal 6 divided by x plus 2 times x minus 3. Okay, let's make it x plus 4. X plus 4 times x minus 3. All right, now remember, you have a polynomial divided by polynomial. Now you may say, this doesn't look like a polynomial. Yeah, it does. If you FOIL this out, you're going to get a quadratic expression. X times x is x squared, the outer and the inner, and then the last. All right, now the good thing is though that this is already factored. Okay, so remember, to find the domain, you got to figure out what makes my denominator 0. Now this is easy enough to where you could look at each factor and determine what numbers make that denominator 0. So you see your denominator is already factored. So if I look at this factor, what makes this factor equal to 0? Well, when x is negative 4, because negative 4 plus 4 is 0. All right, so right away I know that I have to exclude x equal 4, negative 4. Over here, what do I need to exclude? Well, I've got to exclude what makes x minus 3 equal to 0? Well, x minus 3 is equal to 0 when x is 3. So I also have to exclude 3. All right, now remember though, basically what you're doing is you're setting this denominator equal to 0. So x plus 4 times x minus 3 equals 0. And then you're going to use a 0 factor property because you have two factors whose product is 0. So you're going to say x plus 4 equals 0, x minus 3 equals 0, and so therefore x is negative 4, x is 3. And that's what we got here. So the point being that you didn't have to do all this work. You could have looked at this and noticed, hey, this is already factored, so I can just look at each factor and find out what makes this 0, what makes this 0. All right, now, so I found my restriction. So x cannot be negative 4 and 3. Now, here's how you're going to deal with this, though, in terms of the interval notation. All right, so put this in the number line in order. So remember, your negative, you go from left to right, so negative and then positives. So I'm going to put negative 4 first and 3 because negative 4 is less than 3. 3 is greater than negative 4. And then you cross them out. Now notice when I put those two numbers, I have how many intervals? 1, 2, 3. Previously, in these two examples, I only had 2 intervals because I only had one restriction. 1, 2. This, my restriction here was 1/3, 1, 2. All right. So if you look at this, if I had 2 intervals, notice you had, if you had one restriction, notice you had 2 intervals, right? So if you have 2 restrictions, how many intervals do you have? You have this interval, this interval, this interval for your domain. All right, and you just do it like you did before. So you're going to say the domain will be all these real numbers, so from negative infinity to negative 4, parentheses, no brackets because negative 4 is restricted, union, and then from negative 4 to 3, and then union, and then 3 to infinity. So basically what this means is that it's all real numbers except negative 4 and 3. Now in my math lab, they're going to tell you instead of doing union, they're going to say it's separated by commas. So you just put a comma between each interval. Okay? All right, so number 4, let's suppose we had k of x is equal to x plus 2 divided by x squared minus 3x, let's say. Okay, so x plus 2 divided by x squared minus 3x. So again, notice this is a rational expression, a rational function, because you have a polynomial divided by polynomial. Now remember, do I need to worry about what makes the numerator 0? No, because when finding the domain of a rational function, you're looking at what makes the denominator 0. So the numerator doesn't come into play at all in determining what your domain is. Okay? So remember, all we're doing here is just finding the domain. So we got to figure out what makes this equal to 0. So I got to figure out where is x squared minus 3x equal to 0. All right, so let's factor this. So the GCF is x. I can factor out an x. I get x times x minus 3 equals 0. So how many factors do you see? There are 2 factors. There is this factor and this factor. So let's set each one equal to 0. So x equals 0. And over here, x minus 3 equals 0, which means x is 3. So I found the values I need to exclude. So I'm going to exclude these 2 values for x. So before we find the domain in interval notation, let's put this in on the number line in order, 0, 3, and we'll cross them out. So notice that these 2 restrictions separate the number line into 3 parts. Okay, so I'm going to go, so my domain then will be from negative infinity all the way to 0, parentheses, union, and then 0 to 3, and then union, and then 3 to infinity. Okay, so that's your domain. So this says all real numbers except 0 and 3. Okay? All right, let's look at another one. Number 5. Suppose I had k of x equal 2x squared minus 7x plus 4 divided by, and let's say it was, let's kind of figure out one. Say it was 3x squared plus 13x minus 10. All right, so you want to find the domain of this function. Now, first of all, recognize that this is a rational function. Okay, this is rational function. All right, now the other thing you got to remember now is this. The domain of a rational function would be every real number except what makes my denominator 0. It doesn't matter if the numerator is 0. Remember, we can have 0 in the numerator. We just can't have a value of 0 in the denominator. So I got to figure out where is this denominator equal to 0. All right, well, look, what kind of equation do you see here? Well, this is quadratic. That's a quadratic equation. So you can use a quadratic formula, or you can try to factor. Remember, they're not all factorable, so if it's not factorable, you have to use a quadratic formula. But I think this one's factorable, so let's see what we get. We get 3x, x, 2, 5. I think this would need to be negative. This is positive. So let's check it, though. That's 15x, and a negative 2x is a 13x. Negative 2 times positive 5 is negative 10. Okay. So now we're going to use a zero factor property. So I get 3x minus 2 equals 0, x plus 5 equals 0. So notice I have these linear equations now. So adding 2 to both sides, I get 3x equal 2, which means x is 2/3. Over here, x equal negative 5. So 2/3 and negative 5 will make this denominator 0. Okay? All right. Now you can see if you don't believe me, try it. So where we see, let's just check 2/3. Where we see the variable x in the denominator, substitute 2/3 and see if you get 0. Watch. You're going to get 3 times 2 divided by 3, and I need to square that. Okay, so I'm going to square that. Plus 13 times 2 divided by 3, close the parentheses, and then minus 10. You get 0. All right, and the same thing would be true for negative 5, although make sure you put negative 5 in parentheses, just like we did these, just like we did 2/3. All right, so those are your restrictions. So how many restrictions do you have? You have 2. So I have to exclude 2/3 and negative 5. Now remember, though, you want the domain in interval notation. You want the domain in interval notation. So let's put these two numbers on the number line. So I have negative 5, 2/3, just like this. But remember, you always put the larger one on this side, the smaller one on that side. And then I'm going to cross them out to remind myself that I need to not use those. So notice that these two restrictions divide the number line into 3 parts. I'm going to have 3 intervals in my domain. When I do the domain, I'm going to have 3 intervals. Okay, so I'm going from negative infinity to negative 5, parentheses because I can't use negative 5. It makes my denominator 0. Union, and then from negative 5 to 2/3, and then union from 2/3 to infinity. Okay, so that's your domain. So that means the domain would be all real numbers except what two numbers can't I use? Negative 5 and 2/3. Okay, so that should take care of this lesson. Now remember, all we did was this lesson. We found the domain of polynomial functions. So we know the domain of all polynomial functions is going to be all real numbers. Okay, and then we found the domain of a rational function. Now remember, we now know that to find the domain of a rational function, I got to first of all determine what makes the denominator 0. What value of x will make the denominator 0? Then I exclude it, and I use the number line to help me write the intervals. All right, now before we go on, before I end this, let me just show you what the graph looks like. And you're going to graph this in a later lesson. But you do agree that this is a rational function, right? Okay, so let's look at x squared minus 9. Let's find out where this denominator is 0. So notice this is the difference of two squares, so I can factor. I get x minus 3, x plus 3. And then I set each factor equals 0, and I get x to be 3 and x to be negative 3, right? So those are your exclusions. I have to exclude these two numbers, for these two real numbers from my domain. So when we start graphing rational functions, they're basically going to look something like this for the most part. All right? So when I put this on the number line, remember when we put this on the number line? Negative 3, 3, and I crossed them out. And then remember we said the domain was from negative infinity to negative 3, union negative 3 to 3, and then union 3 to infinity, right? So how many intervals do you see? 1, 2, 3. How many pieces of the graph do you see? 1, 2, 3. And I want you to notice this. You see where this, if I trace over this graph, this part of the graph, it goes all the way and it gets close and close to negative 3. So if I were to draw a dotted line like this, you see how the graph gets closer and closer to this dotted line? Now remember, this dotted line goes through negative 3. Okay? Over here, notice that this graph goes closer and closer, and then up here it gets closer and closer to this dotted line. And notice that this dotted line crosses the x-axis at 3. So hence that my domain will be all real numbers. So notice I'm going from negative infinity to negative 3, and then from negative 3 to positive 3, and then from 3 to infinity. So you're going to see how to graph this. It's not difficult to graph, very easy to graph. And most students don't have any issues with this. So that's what the graph of a rational function looks like. All right. So for the most part in this course, this is what it's going to look like. Now notice that there are three pieces because if you look at your intervals, there were 3 intervals. All right. If there are only 2 intervals, then that would be just 2 parts of the graph. Okay. So we're going to see this at some point. All right. So that's going to conclude this lesson.